Hey folks, welcome to Physics 11 Chapter 2. We are going to get into some quote-unquote real physics this chapter when we start looking at kinematics. So in physics, kinematics is looking at how things move. You might have done a little bit of this in junior science. We're starting to look at things like accelerations and talking about objects with different initial and final velocities and talking about how far they travel. It's a fun chapter. And again, we actually get into sort of some more equations, some more math-based application, which is fun. It'll be a nice change. But before we get going, I've been harping on you about units. It was a big part of our chapter 1 test there with frequency and period. And with graphing, we always put units on everything, slopes and slope triangles. I want to take just a moment to talk about the units that we use as physicists. And it turns out there are sort of 3 big units that we use in this course, and then we combine them to make a whole bunch of other units that we use as well. But the first one is, what units do we put on a distance? And you probably know this already. We love meter sticks because we like to measure meters. There's the Canadian spelling, M-E-T-R-E. When you see this little emblem, the thinking cap, that means you don't need to write those parts down. It's just writing things down when you see a little fellow with a pencil, and I'll point him out. So just to give you some history on these units, there's been a lot of time and effort put into a meter stick and coming up with that length being equal to a meter. So I did a little digging, little history lesson here for you, just for fun. The first definition I found from 1791 was, I guess, I shouldn't say discovered. Maybe we could use that word. Discovered by these two fellows. I'm probably going to butcher their names, so I'll just leave it. You can read them. They did something crazy to figure out a meter. They grabbed a crew of people. They hopped on a boat. They sailed from the equator to the North Pole. And then when they got to the North Pole, they took 1/10,000,000th of that distance and said that's equal to 1 meter. Now that was in 1791, and I think they sailed for a couple of years to go there and back. I honestly don't understand how you can sail for several years from the equator to the North Pole and then somehow in the late 1700s, figure out what 1/10,000,000th of that distance looks like. But these fellows did, and that definition of the meter was used from 1791-ish until 1889. And in 1889, I think what happened was people realized that if they wanted to test their own meter against the real meter, they had to also grab a crew of people and sail from the equator to the North Pole and divide by 10 million and risk scurvy and rogue waves and all that craziness. So in 1889, scientists got together and they came up with something different, something a little easier. They put some scratch marks on those metal bars, those picture of the actual bars, and those bars, 90% platinum, 10% iridium, were kept safely in a vault in Paris, a place called the International Bureau of Weights and Measures. And the distance between the scratch marks on those bars, when measured at the melting point of ice, which is 0 degrees Celsius, and you have to be consistent about the temperature at which you measure because metal expands and contracts when it gets hot and cold, and you don't want that to change your meter length. That definition of the meter worked until 1960, until fairly recently. So you could always take your meter stick, and if you wanted it to be really exact, you could go check it against the scratch marks on the bars in the vault in Paris. In 1960, I guess people got sick of having to go to Paris. Be a nice little trip for us. And scientists came up with this definition. Some wavelengths of krypton orange light. A little over 1,650,000 of them. So light travels in a wave kind of like this, and a wavelength would be from there to there. So you measure, oops, maybe I got that right there, I guess. You measure just over 1.65 million of those, and you've got yourself 1 meter. And in 1983, which is when we stopped using that definition, scientists decided they didn't like the krypton orange light. They liked a slightly different one. And they went with the helium neon laser. And it's almost 1.6 million wavelengths of that light. Some crazy decimals on there. Very, very exact, because we want it to be exactly 1 meter. That is currently, you can write that down, there's the little guy with the pencil emblem. That is currently the definition of 1 meter. I 100% do not expect you to memorize these definitions. It's just a kind of fun Jeopardy fact. So a meter, right now, a meter stick is a representation of that many wavelengths from a helium neon laser. For mass, we use kilograms. We don't use grams. That's for the chemists, right? Mix a few grams of this and a few grams of that and see some color change and everybody happy claps. We're like launching things into space, rockets, and we're making race cars go really fast down a track. Those are big things. We like to deal with kilograms as physicists. And this is actually kind of a cool one. This shouldn't say present. This should say 2018. I think I've changed the notes. Is it 2018 or 2019? I think it was 2018. The kilogram was a piece of metal kept in Paris. And until recently, like I had to change my notes for this. I think I've got the updated notes in here, fingers crossed. It was this little, here, let me zoom in on this so you can see it. It was this chunk of metal was the kilogram. It was kept in the vault in Paris where the bars of the scratch marks are, that International Bureau of Weights and Measures. And you triple seal it, so there's a bell jar over top, and a second bell jar over top, and a third bell jar over top, because 3 jars are better than 2 jars are better than 1 jar. And then you vacuum seal it. You suck all the air out, you vacuum seal it as best as you can, so that no contaminants from the air could get on it to make it heavier. Here's what I can tell you about that kilogram. We used that definition for a long, long time. It's kept in a vault with 3 keys that have to be used simultaneously to get into the vault. It's like something out of a sci-fi movie, but it's for real. They would measure the mass every 50 years, and when it came out every 50 years, you could only touch it with the tongs, these special tongs, because if you touched it with your hands, the oils from your hand would get onto the mass, the kilogram, and it's actually had a name, the International Prototype Kilogram, the IPK. But if you touched it and the oils got on it, then it would get heavier, which means every other kilogram on the planet should technically get heavier as well. And because it was the one and only, like that is the only kilogram. Everything else is just a model of that, something that's close. They made 6 sister copies that were as close as they could get to that little piece of metal, the IPK. And some of those sister copies lived in the vault with the original kilogram. And then I believe some of the sister copies went to secret locations around the world, just in case that vault, which is actually more like a bunker underground, just in case something happened and all those kilograms that were inside were damaged. There were some other ones that we could rely on. What's kind of neat, though, is this. In 2018, this is what we currently use. Something a little bit different. It's based on a constant in science, and you use this balance, which uses electromagnetism. This is called a Kibble balance. You can actually look at using Planck's constant and some electromagnetism. When things balance out, you know you've got exactly 1 kilogram. To be honest, I don't totally understand the physics behind this. There are videos, 10-15 minutes long, that you can look at if you want to learn a little bit more. They're pretty darn cool, and that is a very recent change, which I think is kind of cool. Science is always changing and always updating, and I'll say, because this just changed in your lifetime, we get to be part of that update, which is pretty neat. So there's the kilogram based on Planck's constant. Time, we use seconds, just like period, measured from our day, at least before 1967. So you used to play that game where, what's 1 second? Well, it's a 60th of a minute. Well, what's a minute? A 60th of an hour. What's an hour? A 24th of a day. But it turns out that's not right. There's not 365 days in a year because we have a leap year every four years. We have to add an extra day in. So that means every year is actually 365.25 days, and that's because every day is a little more than 24 hours. So eventually things fall off track if you don't account for that. So here's what we actually use for time. We don't use 24 hours because it's not exactly 24 hours. We use this, atomic clocks. So currently, the closest atomic clock to us here in Penticton is, I believe, in Colorado. There's an observatory that has an atomic clock that measures a little over 9.1 billion vibrations of a cesium atom. That's equal to 1 Mississippi. That's 1 second. And then the machine measures that many vibrations again, there's 2 seconds. And that many vibrations again, there's 3 seconds. And that way we always know exactly what time it is. And you can probably appreciate that all clocks, like mechanical clocks, like on a microwave or a stove or even a wall clock, you can set them to the real time, and eventually they're not going to show the right time. I've tried it with watches before, Timex Ironman watches, 2 of them that are almost the same watch. Set them both at exactly the same moment, and after a couple of weeks or a couple of months, they're off by a couple of seconds. And if you didn't reset them again, then they might eventually be off by a couple of minutes, and then they might be off by a couple of hours, and then they might be off by a couple of days. And you'd have to ask yourself, which of those is the correct one? And you wouldn't actually know. Like, was one slow and one fast, or is one accurate and one slow? Is one accurate, the other fast? Who knows? So we really do need these atomic clocks going all the time so that we know exactly what time it is. Now, derived units, you can take meters, kilograms, and seconds. You can just put them all together or mix them up somehow. For example, velocity, we know is measured in meters per second, and that's taking 2 of our base units and just sort of making them work nicely together. Now, types of quantities. I'm going to throw some definitions at you that you do not need to memorize so that you can regurgitate them on a test. You need to know these definitions so that you can answer numerical questions about them. And I'll show you what that looks like in a moment. But first, as physicists and scientists, we measure 2 things. One of them called scalars. So those would be things you would measure that have a magnitude, which is just a fancy word for size, and they only have a size. So they've got some units too. The key here is they don't have direction. So for example, mass, time, temperature, you would never say, oh, it's 18 degrees Celsius west outside, because people would go 18 degrees Celsius west, right? What does that mean? So to put direction on a scalar just makes it nonsensical, so we don't. That's what makes these things scalars, as opposed to vectors, which are measurements that do have a direction in addition to a size with units. So those are examples like velocity and force. And quite often we will, especially in this chapter, just stick with like positive versus negative. Positive could be to the right or up or east, something like that. Whereas a negative means to the left or down or west or south, I guess. So you're implying a direction on every vector that you write down, even if you weren't thinking about it as the person writing the number down. So you have to be a little bit careful. We won't really start playing with compass directions until chapter 3. So it'll be one of those kind of hold those thoughts or hold that thought. So here's some definitions you need to know just so that you can actually answer questions about them, not regurgitate them. So position is the location of an object with respect to. WRT stands for with respect to, some reference point. So you decide where you're going to put 0, where you're going to put the 0 on your tape measure, and you measure away from there. That would be like saying, oh, the ceiling is 3 meters tall. You'd probably have the reference point be the floor in the room that you were measuring from. So position is a vector, so positive versus negative matters. There's a couple of symbols that you might see in physics. We typically will use the D, but sometimes people will use an X and an S. All vectors should have little arrows on top of them just to identify those measurements as vectors. We don't always do that in Physics 11, so we won't always have to put these little arrows on top of the symbols. And the location of an object, we measure in meters. Those wavelengths of the helium neon laser. So for example, let's say the tractor's sitting right there. We've got like a nice, maybe the tractor's parked on the road. Somebody's sketched out a nice big meter stick there. And we want to know where is the tractor sitting relative to the reference point, which we're going to call 0. So let's just ballpark it. The object is at position 3 meters. Now what I want us to do in this chapter and every chapter moving forwards is I would like us to make all final answers 2 or 3 sig figs plus units. So we're going to relax on the counting sig figs and counting decimal places rule, and we're just going to go 2 or 3 sig figs plus units. So I don't want to say just 3. I should actually say or write down 3.0 m for meters, just as a ballpark measurement. Displacement is how an object's position changes during a trip. So it's a vector. Direction matters. There's a couple of symbols. It should, I guess, technically be the little delta triangle sign with the arrow on top of the D, the change in position, although we're just going to put D just to make life easy. Units are meters as well. And what I want you to always remember for displacement, all you care about is where did the object end up compared to where did the object start. So what is its final position? And you subtract its initial position. You don't worry about what happened in between. You simply look at the end and you compare it to the start. That's it. Don't worry about the middle of the video. So this tractor goes forwards, goes backwards, goes forwards again. We're not going to count this movement as anything. It's just to show that it goes forwards a few meters, backwards a few meters, forwards a few meters. We want to figure out the displacement of the tractor. So it finishes at 5 meters. It started at 3 meters. The difference between those two, time is going to be 4 seconds. We'll need that in a little bit. But just for displacement, it is positive 2.0 meters. You don't have to put the positive sign. If you write it like that, we assume it's positive. That's probably how I would recommend writing it, to be honest. But all we cared about was the end position compared to the beginning position. We didn't worry about the forwards and backwards in between. Contrast that with distance, which is like just how far have you gone overall, the total amount of travel. It's a scalar. There actually is no symbol, so you should write the word distance, although I'm okay if you write down just D-I-S-T, dist. And the units are meters. So again, the kind of question I might ask you is, what's the displacement of the tractor? You have to know the definition to get the number answer. And then I might say for part B, what's the distance the tractor traveled? Well, now you do have to count the forwards and the backwards and all the in-betweens. So it goes forwards 4 meters, backwards 6 meters, forwards another 4 meters. That gives us a final distance of 14 meters. And 2 or 3 sig figs, it could just be 14, or you could call it 14.0 meters. Either one works. So, taking those two ideas, keep them in mind because you're going to need them. Velocity is how quickly your displacement occurred, the rate of change of your displacement. V for velocity, it's a vector. The symbol should be a V with a little arrow on top, but we're just going to use a V instead. We'll skip the arrow. And here for units on velocity, meters per second. The equation to calculate velocity, and it's technically an average velocity, but you can just think about it as velocity. It's displacement divided by time. So that D, remember, is displacement. Now you have to remember what displacement is to be able to figure out velocity, right? You can't get mixed up and put a distance in there. So if we do that calculation for our tractor, the displacement was 2 meters divided by, we had said it takes 4 seconds for that tractor to do its movement. So 2 divided by 4, 0.50, make sure you get your 2 sig figs, meters per second. So that's the kind of question I might ask you on the Chapter 2 test is, give you a little picture and say, what's the velocity? Well, you even have to know what velocity is as well as displacement in order to get that. Contrast that with something more familiar, which is actually speed, more commonly used. Speed is actually the velocity kind of without the direction piece. This is the better definition though, this one here. It's the rate of change of the distance. So the big change here is speed is your distance divided by time. S for speed, S for scalar. The symbol could technically be a V without the arrow because that would be the non-vector version, but we're actually just going to go with the word speed. Base units we like are meters per second. So the equation now is that your speed is distance divided by time. So you have to remember that difference between displacement and distance. For our tractor, what did we say? It was 14 meters distance in 4 seconds. So that's going to give us an average speed of 3.5 meters per second. So again, don't memorize to regurgitate, memorize definitions so that you can understand what the numerical answers might be. An important conversion, speaking about speeds and velocities, is this one. How do we go from kilometers per hour into meters per second again? And here's the long way, the conversion factor method that we chatted about in chapter 1. Convert kilometers into meters, convert hours into seconds, 72 times 1,000 divided by 3,600. You type that in your calculator, you get 20 meters per second. Is there a shortcut? Yes, there is. To get from kilometers per hour into meters per second, divide by 3.6. You're going to want to memorize that. I would actually memorize this. Kilometers per hour into meters per second. This will save you a lot of time if you commit it to memory. If you want to go that way, divide by 3.6. And sometimes you'll actually want to go from meters per second into kilometers per hour because that might make more sense to picture how fast something is going. You simply multiply by 3.6. So there's a conversion that you're certainly going to want to memorize in order to quickly move through some of the questions that we'll see in this chapter. And let's finish it off. Let's make sure you understand the difference between displacement and distance. So this first scenario, I'll number them just so I can talk about them by number. Scenario 1, the tractor travels just to the right, some distance, goes from, I guess, 1 to 6. That's a displacement of positive 5.0 meters. For distance, it's positive 5.0 meters, 2 sig figs or 3 sig figs plus units. Your distance and your displacement are the same in scenario 1. Maybe I'll just write it in. 5 meters to the right, distance 5 meters. So you actually end up with the same value when the object moves in a straight line, but only if it's in the positive direction, which is kind of weird. Because look at the difference in scenario 2. Here the tractor goes backwards or to the left from 6 to 1 meters, which is a displacement of negative 5 meters. Remember, direction matters for displacement, but not for distance. Distance is always positive values. So you say, well, what's the distance it covered? Well, it covered a positive 5.0 meters because distance is always positive. It just moved 5 meters. So we can say that distance and displacement are the same for an object if it moves in a straight line in the positive direction. If it moves in the negative direction, things are going to be different. And when we get into something like scenario 3, as soon as we start going in multiple directions at the same time, now they're for sure going to be different. Displacement, here we start at 1 meter, we finish at 3 meters. So that's a displacement of positive 2 meters. We end up 2 meters to the right. But how much distance did we cover? 1 to 7 meters is 6. And then it looks like we've gone backwards another 4. From 7 to 3. You don't count positive versus negative, you just treat it all as positive. This thing has traveled overall 10 meters. And in scenario 4, kind of a neat one, we have the tractor starting at 1 meter. It goes forward some number of meters and backwards the same number of meters. It starts and finishes in the same place. No displacement, 0 meters. I won't be super picky about 2 or 3 sig figs on 0 meters, although maybe it's a good habit to get into. So maybe let's put it at 0.0 meters. What about the distance? Well, it traveled forward 6, it traveled backward 6. That is going to be 12 meters distance in total. Your homework that goes with this lesson, hopefully that wasn't too quick. The homework that goes with this lesson, I need you to plot the data points on the document you'll find in the All Resources folder. It's called Worksheet 1. It's a couple of graphs. I need you to plot the points on the graphs. And don't even worry about drawing lines. Just plot data points. There's actually two graphs, and each graph will have two sets of data points. So your first graph will give you something like this, where there's one set of data that looks like that and another set of data that looks like that. You can see two different trends happening. And then you're going to see that on the second graph as well. You'll see, I think it's something that looks a little bit like this, but I want you to go and plot those data points. That's going to be one set. Here's the second set. Looks like that. So plot those data points. That'll get you ready for lesson number 2, which will be the next video on the website. Next one in line. Have fun plotting data points.